today I will be discussing some of the work that has been done on the eye process. So I have to say that the merit goes to Arthur Chopin, did most of the work. I'm just here to relay what he's been doing for the past 3 or 4 years. This work is also in collaboration with Stefan Gorioli, provides great input in nuclear physics, as well as Sébastien Martinet, who's a new postdoc in our group. So I will just, even though this is the home of AGB star, just give a very brief recap on the AGB evolution, so you know, because I will be talking a lot about nucleosynthesis. So AGB stars are lone intermediate mass stars, typically between 1 and 8 solar masses. They have completed their helium-burning, so they are made of a CO core, you can see on that sketch. And there are 2 layers. There is a helium-burning layer, there is the hydrogen-burning layer that you can see here. On top of that, a very expanded convective envelope. And what is very interesting in AGB stars is the rich nucleosynthesis that can take place. So what happens is that during the evolution, during this last phase of evolution before the star becomes a white dwarf, you have instabilities, convective instabilities, the great things you can see here, those thermal pulses that appear regularly during the AGB evolution. And during these instabilities that take place in the hydrogen helium-burning shell, then a lot of energy is released, and that lifts the convective envelope. As you can see here, it's lifted. And eventually, when the instability decays, well, the envelope falls back and enters the region that was previously occupied by the pulse. And this is called the third dredge-up. So you go inside the star, and this is the way you can enrich the surface with the products of the pulse nucleosynthesis, but also heavy elements. And basically, this is thanks to these dredge-ups that you form carbon stars, that you enrich the envelope in carbon. And so those elements pollute the envelope, and eventually, via the strong winds that develop during the AGB phase, all these elements are distributed in the interstellar medium by the stellar winds. And they contribute, of course, to the chemical evolution of the galaxy. AGB stars are known for producing some carbon, but also some heavy elements like the S elements that we'll talk about. So AGB stars are able to synthesize heavy nuclei. By heavy, I mean more massive than iron, by the so-called slow neutron capture process. So this is a sketch of how this happens. So you have some stable elements. This is the value of stability. And here you have some neutrons. So let's say you start from xenon, you capture neutrons, so you form all the stable isotopes. And then you enter in here, this xenon 133, that is unstable. And if the time scale for beta decay is shorter than the time scale for neutron capture, then you form that element and it will decay, and you form cesium. And by this process, you progressively populate all the value of stability, and you form those heavy elements, but you need neutron sources for that. And in AGB stars, there are 2 main neutron sources for the S process. The first one is, the first I mentioned is the neon 22 alpha N reaction that takes place in the convective pulse. This one is characterized by the fact that it requires high temperatures, above typically 350 million degrees. Neutron densities are typically of the order of 10 to the 10, 10 to the 12 per cubic centimeters, and a pulse lasts about 100 years. So it's short duration. And it mostly produces, because these neutrons are released in the convective zone, it mostly produces light S elements like strontium, yttrium, or zirconium. But there is another source of neutron that comes from the C13 alpha N reaction. And there, that's a little bit more complicated, but it gives rise to a richer nucleosynthesis. So to trigger that reaction, you need to invoke some mixing processes. So this is the sketch of our AGB model. So you have the thermal pulse, in which, you have 3 alpha reaction that produce some C12. So you see the yellow region is after the decay of the pulse, that all these layers are enriched in carbon. And then you have this third dredge-up that comes into play. And at the deepest extent of the envelope, if you have some diffusion, some mixing of protons in the carbon-rich layer, then you can have that chain of reactions. These protons that are captured by the abundant carbon, they produce some nitrogen 13, and that decays into C13. And in the top of that layer, we still have a larger amount of carbon that can proceed to the complete CN cycle. So you form some nitrogen. But below that, because there are fewer neutrons, protons, you're left with the C13 that will burn reactively with the remaining alpha particles and give rise to these neutrons. And using that source of neutrons, you can produce heavier elements because the irradiation lasts for a much longer period of time. So you release neutrons for typically 10 to the 4th years, it's quite long, and you build heavier elements like barium, lanthanum, or even lead in low metallicity stars. And well, this S process works pretty well. I mean, it has been, this is an example of an AGB star, and so in blue, this is the R process. I will come back to that later. Distribution, the solar R process distribution. And in red, this is the results of one simulation. And you see that we can fit most of the data points pretty well, including the production of lead. Also, when we observe low mass stars at low metallicity, we find that a large fraction of them are enriched in carbon, these so-called CNP stars, for carbon-enriched metal-poor stars. And there are different classes of CNP stars. Some of them are enriched in S-process elements, like those. Here I show, so this is the abundance of barium. Barium is a tracer of the nucleosynthesis, of the S-process nucleosynthesis. And europium is more a tracer of the R process. So you see that stars which are enriched in barium, but moderately in europium, they can be reproduced by the models. All the symbols you can see are evolutionary tracks, like the one computed here at Monash, and they go through the observation. So we can reproduce these guys. So AGB models, we can fairly well understand and reproduce these abundances. But there is a problem. You see with these, green observations, and those are the CNP RS. So RS, because it's a mix of R and S, and you see they are much more enriched in europium. Europium over iron is typically of the order of 2. And AGB models cannot reach these guys. Well, maybe a little bit those, but the majority of the observation, they cannot be accounted for by the standard S process in AGB star. So how can we form those elements? Well, you can say, well, it's a mixture of S and R. But as I will show, it does not necessarily work. You can assume a prime model pollution. Or it can be something intermediate, because we have on one side the S process, which is relatively low neutron densities. We have the R process, very high neutron densities. And then maybe a process in between that would produce those elements. Because if we want to produce europium, we need higher neutron densities. And this is where came the idea of high process. So, as I just said, depending on the neutron density, which is shown here in this axis, we have the S process that I mentioned in AGB stars, so neutron density between 10 to the 6th and to the 10/12th. It's a long duration, that's the radiative S process. We have the R process, then you can reach very, very high neutron density, above 10 to the 24th. It lasts for a very short period of time, and is typically in dynamical events, like neutron star mergers or supernova explosions. And you have the intermediate process, this so-called I process, with neutron density typically of the order of 10 to the 15th, and the time scale is typically a day, as I will show. And in this process, to activate this I process, as I will describe, you need to mix protons into a convective helium-burning zone. I will describe all these processes, and that's what we often refer to as proton injection events, PIE. You will see that term very frequently. And neutrons, as I will describe, they are produced the same way as during the radiative S process. So first, when these proton injections, they have been numerically observed in various simulations. And especially in low mass stars. And well, Simon's thesis is full of these injections, proton injections. That can happen. This is the evolutionary track of a low mass star. And the red is the the red giant branch. So it can happen at the tip of the red giant branch during the core helium flash. And Simon showed that you can have this proton injection. It can also happen at the early stage of the AGB phase during the first thermal pulses, but usually that takes place at very low metallicities. And also that can happen much later once the star has almost become, well, is on its cooling track, on its wide dwarf cooling track, when you have a late thermal pulse. And this is the so-called Sakurai objects. And those objects have the last pulse that will bring those stars back into the AGB phase, and they will do some loops, and they also have some of these proton injections. And this is typically what you observe. This is some of Simon's simulations. So this is during the core flash, where you have the helium flash, and then you have some injection. There is the envelope that does some weird things that grows, and here you have some injection of protons. Can happen a little bit later, also during the early AGB phase. So those processes have been witnessed. More recently, a new site for proton injection has been discovered. Is during the accretion of material onto a wide dwarf. So it's like a nova-like event, but depending on the accretion rate, you can have this proton injection. And this is what you see with these purple lines. This is the cycle when you have these nova cycles, these nova explosions at the surface of the wide dwarf. And during those, it's like a flash, a thermal pulse, you have some proton injections. But it also happens in more massive stars. It happens, for instance, it's in super AGB stars. So super AGB stars are the stars that make the transition between AGB and massive stars. So they ignite carbon off center, as you can see here. Then it's a little bit complicated. You have some flame, and eventually the more massive ones, in the helium-burning shell, there is a convection zone that grows and eventually merges with the envelope. And you see here there are a lot of lines, means that the computation was quite tough, but that's where the proton injection takes place. So you have also, that also happens in some super AGB stars, but it's really limited to a very narrow mass range. So you don't expect those stars to contribute to the production of these high process elements in a substantial way. And also it has been found in more massive stars, but also at very low metallicity. So mixing of protons between with the helium-burning layer. The work I will present, the calculation I will present, they have been made with the code I've been developing for decades now. Which is called STAREVOL, and the major upgrades were especially dealing with the nuclear network, because if you want to compute the nucleosynthesis of the high process, as I will show you, you may even form some actinides, so like uranium thorium, so it's very heavy elements. So you need a very extended nuclear network, and it is shown here. So it typically involves almost 1,200 isotopes, coupled with we don't need so many reactions because it's mostly neutron captures and beta decays. We don't need too many reactions, but still more than 2,000. And to calculate those events, what needs to be done is to couple the burning and the mixing. You cannot dissociate both because everything is a similar time scale. The mixing time scale is about the same as the burning time scale. So you can't say that the composition is homogeneous. When your particle is traveling, then it's burned on the fly. So you have to couple the mixing and the burning at the same time. So that makes big matrices to solve, but now there are algorithms that can deal with that. So this is the evolution of the abundances. So this is the diffusion term, and this is the burning term due to the nuclear reactions. And in this diffusion coefficient, we include, of course, convection. We can also add any other kind of processes like overshooting or mixing due to rotation or whatever. And we have investigated stars in the mass range between 1 and 4 solar masses, and metallicity between Fa over H between -3 and 0. Okay, so I will show you how it happens in a representative case. So it's a 1 solar mass star with a metallicity Fa over H of -2.5. so it's a low metallicity, and the fact that the metallicity is low is important because in the first pulse, this is the first pulse, so it's a function of model number, it's not time. And this is the mass coordinates, and the shaded regions represent the convective zones in the star. The green here is the hydrogen burning shell, and the blue here delineates where helium is being burnt. The dotted line is where the nuclear energy production due to helium burning is maximum. Dotted green line where nuclear energy production due to hydrogen burning is maximum. So in the first pulse, well, the pulse is relatively weak initially. And there is a chemical gradient between, this is the helium layer, this is the hydrogen burning shell, so there is a chemical gradient. And at low metallicity, this gradient is shallower, because you don't have all these metals that contributes to build up the mean molecular weight. And what happens is that, well, initially the pulse is too low, and you cannot cross the so-called entropy barrier between below the hydrogen burning shell. But when you go to the second pulse, it is much stronger, and then the convection is able to penetrate into the hydrogen burning shell. So what happens? Then the protons that are in the hydrogen burning shell, they start to migrate due to the convective motion inside the pulse, and they are burned on the fly. So that's why you need to couple burning and mixing. And while the protons that are captured by the abundant carbon in a thermal pulse, that produces the nitrogen, and nitrogen then decays in something like 10 minutes to produce the C13. So eventually, C13 is able to reach the bottom of the pulse here, okay? And there you can have the C13 alpha reaction occurring and releasing a lot of neutrons. But the thing is that where the neutrons are released, the temperature is much higher than in the radiative conditions. Here the temperature is of the order of 250 million degrees, while during the radiative process, typically 90 million degrees. And you know all the nuclear reaction rates, they depend very strongly on the temperature. So you can, for a very short period of time here, typically during a day, release neutron with a density of 10 to the 15th. And it is those neutrons that will be able to produce all these elements. And protons, they are dragged down in the convection zone. And the thing is that, so typically the typical convective time scale is of the order of 1 hour. But the burning time scale of the C12 P gamma reaction is, let's say, a day at the bottom of the hydrogen burning shell, but it's 1 second at the bottom. And there is a place inside the pulse where the convective and burning timescales are equivalent. And this is where most of the energy is released. So eventually, inside the pulse, you can see the nuclear energy that is deposited at a given mass coordinate, and it's going to be here. So energy builds up, is accumulated here, and what happens is that a temperature inversion takes place. And you maybe remember from your classes of stellar evolution, but if you use the Schwarzschild criterion, and if you have a negative temperature gradient, it means that the shell becomes radiative. So because you build up that temperature inversion, then suddenly some radiative layer appears here. So that's where the pulse splits. You can see that there is a lower tongue here, and there is stuff above that remains convective. But the two are now disconnected. Okay? So in the bottom layer, nucleosynthesis still proceeds, but it will never reach the surface. But at the bottom, what happens eventually is that you see, because of the large amount of energy that is released, there is a reaction of the star, and the convective pulse grows in mass and eventually here merges with the envelope. So all the high process elements that have been produced at the base of the pulse, they were mixed into the convective envelope, and eventually they can reach the surface of the star. So what happens next? Well, it depends on the mass of the star. So this is the evolution of that one solar mass star. And this is the proton injection event. And during that event, you will dredge to the surface a lot of carbon, well, some high process elements, but mostly some carbon that is produced during the pulse. and that will considerably increase the metallicity. You remember that we start with a very low metallicity star, so as soon as you have primordial carbon, then the metallicity increases. You can start to form molecules, like CO molecules, and that will dramatically increase the opacity. And if you increase the opacity, well, the gas, of course, more opaque, and so the star will start increasing in radius, and the massless prescription, it typically depends on the luminosity, meaning on the size of the star. So because after that mixing event, the change in the envelope composition will be such that the massless rate will be increased by a huge amount of time. And that produces, the removal of the envelope before the next thermal pulse can happen. So the evolution of the AGB is truncated, okay? So there are no more thermal pulses. But this is different if you use a more massive star, because we still have this proton injection event here. But because here you have 1.5 solar mass of envelope as compared to 0.5, the dilution factors are less, so the enrichment in carbon is less, so the effect on the mass loss is less, and you can have subsequent thermal pulses, as you can see here, with trade-offs before the end of the AGB. So for those stars, they resume kind of a normal evolution after this proton injection, except that the envelope is now polluted with these heavy nuclei. Oops, strange. So how does that those proton events depend on the metallicity and the initial mass of the star? So this is what is shown here. So this is the initial mass, this is the metallicity, and what we see is that, and the different symbols refer to different simulations, different works. Well, the blue ones are for Simon. Let's see the blue here was dealing especially with, very low metallicity stars. And what we see is that it's limited to low mass stars, typically less than 3 solar mass, and metallicity, very low metallicity. The spread you can see is partially due to the fact that some people also included some extra mixing in their simulation. And this is what we wanted to do with our code. So we have a consistent set of models to see what is the influence of adding some additional mixing in the star. And this is what we did. So we implemented overshooting. So overshooting is typically when you have a convective boundary. What the Schwarzschild criterion tells you is that the acceleration is 0. It doesn't mean that the velocity is 0. So if you have blobs of material, the acceleration is 0 at the Schwarzschild boundary, but they still have some velocity. And the inertia can make, some extra mixing beyond the standard boundary. And there are various ways of modeling it. What we do is use an exponential decay of the diffusion coefficient. And it's characterized by this parameter F, and HP is the pressure scale height at the convective of the... Yes, Alex?
Finish the sentence. Finish the sentence first. I interrupted you a bit.
Right. It's a small decay of the diffusion coefficient at the edge of, at the convective boundary.
Yeah. So formally, according to mixing length theory, the convective velocity is 0 at the convective boundary. So that formally, the convective boundary is 0, so then this formula comes. So you have to choose something else. So you can't take the value of boundary of the convection zone.
Well, in my case, I don't have 0 at the convective boundary.
It should be, according to mixing length theory, it should have.
It's the actual. I know that people have claimed that, but I did not find that.
If numerically not, because you don't resolve it, but analytically it should be.
Could be. Yeah, could be.
So you have to pick up something inside the convection zone, and then it's something like that. Then you make a choice.
Yeah.
Mm-hmm.
Yeah, well, nevertheless, it's all inserted, not resolved. And so what we did is to include overshooting at the various convective boundaries we have. So remember these convective events we have. So what we did is to include overshooting below the convective envelope below the convective pulse and at the top of the convective pulse, just to see how that affects the evolution. So if we include overshooting below the envelope, so this is the resulting chemical composition, just to show if that affects. So the black line, if we set f1 to 0, we do not take into account overshooting at the base of the envelope. And the red, all the other ones, they are underneath that line, so it gives the same, so it has no impact. We did the same below the pulse. We see slight differences in the resulting nucleosynthesis, but well, it's not very big effect. But if we include some overshooting at the top of the pulse, that's where things becomes very more sensitive. The first thing is that if we include this mixing at the top of the pulse, we see that first the chemical, well, of course, the chemical profiles will be smoother, and that can translate in the less. The fact is that we remove these energy spikes. I recall you that those spikes, they correspond to where the nuclear energy, where is the maximum nuclear energy production by hydrogen burning. So you see that if we don't have some mixing at the top of the pulse, as soon as we inject a shell, then, well, we inject a little bit of protons, they get burned, but not enough. So progressively, because it's discrete, we add more shells, and progressively, eventually we end up at the very beginning, so it's discrete. But if we smooth the profile because of that diffusion process, we see that the energy profile gets much smoother. Okay, so that's the first effect, is that it smooths down this proton injection. The red color here corresponds to the overshoot region. So here there is no, it's small and much bigger. But the other impact of adding this mixing at the top of the pulse is that it shortens the event. What is shown here is the maximum neutron density reached during the event. So you see that we reach typically 10 to the 15. It depends a little bit on the value of f-top, but not so much. But what we see is that if we don't have this extra mixing at the top of the pulse, we have this burst. And the entire event lasts much longer than if we increase that mixing. And that can have some impact on the nucleosynthesis. As you can see here, for instance, the element between Z, between 35 and 55, the abundance is changed if you change the mixing parameter. Also the actinide, but I will come back to that later. But most importantly, it changes where these proton events happen. So this is the same plot as before. This is the initial mass. This is the metallicity. The gray area was typically what I showed you before. So what we had without mixing. And now if we start including mixing with a small value of f-top, we get the green area. Then if we increase again the mixing at the tip of the pulse, we enlarge that region. And for very large values of overshooting at the top of the pulse, we see that even at solar metallicity, we can induce some proton injection events. And also more massive stars gets, potentially get some events. So that can have some impact on the production of those elements in terms of chemical evolution of the galaxy. So now I will discuss a little bit more about the nucleosynthesis. What are the elements which are produced? So this is a chart of nuclei. So you have the number of neutrons, and this is the number of protons. And this is in blue, this is where the R process takes place. Okay, so you have very high neutron fluxes. So if you start from a stable element, then you will go here to the drip line. Neutron drip line means that on the other side it's unstable. It falls back into that plane. And all the elements focus on that drip line. And eventually, if you turn off the neutron source, all those elements, they will decay back onto the valley of stability. So this is how you produce some specific Elements like these actinides here, uranium, thorium, they require very high neutron densities, and they were thought to be only formed by the R process. The I process is the green one. So it's very close to the value of stability, which is represented by these black squares. But you see, well, it starts to get a little bit in the neutron-rich area. But yeah, it's closer to the I process than to the R process. And this is a typical path. This is a zoom around the iron. So this is the S process path with neutron densities of typically 10 to the 8th. So you follow the value of stability. The R process is way to the right at larger neutron numbers. And this is the I process. So you see we're not too far, but we start producing very neutron-rich isotopes. And for instance, this is what is shown here. So this is the atomic mass. And let's take just europium, because this is the tracer of the R process. So you see that during this proton event, we'll be producing the neutron-rich isotope of europium. All of them are unstable. The stable ones are the 151 here and the 153. So we produce these guys here, which are very unstable, and then they decay, and they will produce those guys. So all the elements, we produce the most massive isotopes. And eventually, when the neutron density, when the neutron flux stops, they will decay and start populate the stable isotopes.
Sorry, but
yes.
You don't produce you show the unstable europium, but it's not the unstable europium that decayed europium.
No, that's true. You
know exactly the lines.
Exactly. No, it should be at constant A. Yeah, you're perfectly right, Alex. Yeah. And so also we compare what is really the difference between the S and the I process. Okay. So this is in blue. This is the typical S process abundance for a star with a metallicity of, well, F over H is minus 2.5. And in black, this is what we obtain with the I process. And the star, HC blah, 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 is CMP RS star. So this is one of the stars we tried to fit to see if our models were able to reproduce the abundance distribution in that star. And you can see that it does a pretty good job and much better than the S process, which is the blue curve. Especially, you see the europium is overproduced. Tantalum is largely produced, but we can't observe it. Well, we still produce barium, some xenon as well. But the main difference is also that at the S process, you also produce some light S process element like strontium, yttrium, or zirconium, which are here, and that those are not reproduced by the blue line by the S process. So there are some differences, and we can distinguish between the two processes. We looked, well, mostly Arthur, looked at the chemical fingerprints. What are the main elements that show up when you do the I process as compared to the S process, and see that there are a few isotopes that are much, which are overproduced compared to the S process. So you see, for instance, the barium 137 is largely produced during the I process, and well, it's about almost 0.5 dex. The enrichment is 0.5 dex higher for that element. We've got also other elements. So we looked for all the possible candidates that could identify the I process. Something interesting now that we looked is that the production of these actinides. So actinides is these elements that you can see here, very high Z and neutron densities. And usually the S process cannot produce those elements. And the S process typically stops at bismuth here. Because what happens is then, well, the decay timescale here is relatively short. And usually what you end up is forming bismuth, and you stuck here. Or if you stop in this way, then what it does, it eventually reaches that yellow region, deadly region, because that's alpha unstable. So I mean, as soon if you have an element here, that decays will go here, and then it will enter that part. And if it enters that region, it will emit an alpha particle and go down back here. So you're stuck. And you can see here the different lines on different paths, different shells inside the pulse. And you see that sometimes it loops. You cannot, for instance, this line, here we reach that region and we stuck. We can't go even further. You really need the highest neutron density so we can go here and then eventually, well, we bypass that yellow region because that's deadly. And then when we've passed that, well, then we can continue. That's fine. And eventually, when we stop the neutron flux, all those elements, they will decay into, let's say, uranium. So it's this one that will decay to uranium. And we can produce also some thorium here, okay? But the thing is that producing actinides it depends very, very much on the nuclear physics as well as on the mixing processes. So there is only one CMP-RS stars which have some detected thorium in it. So we say, well, let's have a try and see if one of our models can reproduce the abundances. So this is what is shown here. And so this is thorium. So we see the different lines correspond to different nuclear input models, basically different N gamma rays. And we see that we can reproduce some thorium, some thorium. We can fairly well reproduce, the heavy S elements here. Lead slightly overproduced, but well, we still have problems with the light S elements. But we're happy that we could reproduce that because those elements, they were only thought to be produced during these either neutron star merger events or supernova explosions. But potentially AGB stars could also produce these elements. Of course, we studied, because we run those grids of models with different masses and different metallicities, we can determine what we call the yield. So it's the production of elements that, the amount of elements that is released by one star in the interstellar medium. And the composition is shown here. So for the I process, it's a bit similar as for the S process. At low metallicity, so this is the red line, as you can, or the black line here, there is a lot of iron. So as soon as you release neutrons, they will be captured by iron. So most of them are captured, so you can't grow to bigger elements because there is so much iron. But if you go to lower and lower metallicity, you have less and less iron. So you start building up bigger and bigger nuclei. And eventually, at very low metallicity, you produce a lot of lead, which is this line here. And we see that typically when the metallicity decreases, you start producing more and more of these massive nuclei here, or heavier nuclei. The same for the two solar mass. There are slight differences, but the overall picture is the same, and it's very similar behavior to the S process. We also tried to compare our models with a sample of CMP stars, and so those are the stars we selected. They have about the same metallicity. They are low metallicity stars. And this is the chi-square. So we compared the abundances of various elements and we calculate the chi-square and to see what is the minimum. So we used the green line is the R process. The black line is a pure S process. And the red is our I process elements, and in blue it's a mix, because sometimes, as I said initially, if you have CMP RS stars, you can say that the R component comes from a primordial pollution. You had, let's say, massive stars nearby, they exploded, polluted the cloud out of which the star was formed into these R process elements, and you can see them now. So they are not produced by the star, but it's a pollution, primordial pollution. And this is the blue line. This is this scenario. And what you can see, basically the smallest chi-square, except maybe for one or two stars, is best reproduced by the I process event. So it seems that to give credit to that process, and at low metallicity it seems to work relatively well. And also, because we are dealing with CMP stars, so those are old stars, polluted in heavy elements. They are typically main sequence stars. So it means that they inherited their composition from a pollution by an AGB star, which is now dead. And we have some dilution factor. How much of that AGB high process rich material should I dump into that small star to reproduce the level of enrichment? And if you do the math, we find that typically 0.05 solar masses of the AGB mass should be accreted by the CMP star to reproduce the observation. And this is not a crazy number. This is kind of realistic. We also compared our results with more metal-rich stars. So we looked into database and searched for stars with metallicity between -1 and -2. And those are the model predictions, and those are the observations. So the blue points should be compared with the blue lines, the red points with the red lines. So basically, except maybe for a few stars like this one, we can reproduce the scatter of abundances in those, even in the more metal-rich stars. Okay, so indicating that, in fact, high process may also, from an observational point of view, is consistent with, high process is consistent with the observation of more metal-rich stars. But what I forgot to mention since the beginning is that there are huge uncertainties, many uncertainties. As soon as you do a 1D star, there are uncertainties everywhere, but especially concerning the high process, the nuclear uncertainties. So if you take different assumptions on nuclear input physics, then we can have large variations on the estimated abundance nucleosynthesis. And this is what is shown here. So between the blue and the green line, all the points here are different nuclear models with different input models. And you can see that there are very large, there is quite a large scatter between 0.5 and 1 dex of uncertainty in the abundances just due to the nuclear models. And it's even worse for the actinides. Because in these guys, as I showed earlier, there are plenty of reactions for which we don't know the rates. That could go wrong here and bring your particle back into this deadly yellow region, and you kill the production of actinides. So the production of actinides is very sensitive, extremely sensitive to the nuclear properties. But also, as I mentioned in the very beginning, also on the assumption of mixing. Remember that there was one of the first slides. If you change the value of the overshoot at the top of the convective pulse, then it impacts the production of intermediate mass elements, but also of the actinides. And you see that if the overshooting is very strong at the top of the pulse, we produce almost no actinides. Okay, so both nuclear uncertainties plus mixing, not speaking of observational uncertainties, which are even bigger. No, I'm teasing them. It's hard to predict. Okay, so I come to my conclusions. So we've investigated the proton injections in AGB stars. And it's typically limited to low mass stars, typically below 3-4 solar mass stars. And it's very dependent on how you treat mixing at the top of the pulse. If we compare the nucleosynthesis, what we see compared to the S-process nucleosynthesis, the I process underproduce the light S elements and tend to overproduce some heavier elements with Z larger than 50. With this scenario, we can explain many of the CMP RS stars. We don't need an extra parameter of adding an initial composition, initial pollution. It gives quite good results without tweaking too many things. A new result is that this I process could be also a source of this production of thorium or uranium, not only the energetic events. And nuclear uncertainties are very important. They have a very strong impact, as well as the way you model the mixing. And that brings to, of course, we always need better prescription for those mixing. This is just ad hoc. And we hope that eventually hydrosimulation could help us, constrain a little bit more that mixing, because this is what gives the I process. And I stop here. Thank you.
I've got a question, two questions actually, about sort of the two tracks you showed for the S process and the R process.
Yes.
I process and R process. So obviously the R process track is also, got significant nuclear uncertainties, and so I was wondering, because I've seen, tracks that get much closer to the value of stability, particularly for higher electron fractions. So I'm guessing this one is for a lower one. So I was wondering, how does that change the ability to distinguish between I process and R process for different tracks of R process in particular?
Well, that will mostly depends, well, the electron density is important, but mostly the neutron density. How far you go from the value of stability. If your neutron density is not too high, then, well, potentially you will follow the I process path. That's what makes the difference.
So then I've got a follow-up question about, have you thought about whether this potentially at all helps alleviate the concern with R process and neutron star mergers in particular, explaining the chemical enrichment of certain stars, because they need some sort of delay, and if I stars or AGB, I process through AGB is filling that gap.
Well, I haven't thought of it, but it also depends on the time scale, because AGB stars are relatively low mass stars. They take long to die, even though we saw that the evolution can be truncated because of these events. No, I haven't thought of that, but that's a good idea.
So usually in this convective envelope, this is often driven by the iron peak as the key source of opacity. But in these neutron star mergers, we've seen there has been lots of issues about these extremely high opacities of these lantanides and actinides which you produce in your S process. Mm-hmm. So if you now enrich your envelope in these heavier elements, will this affect the envelope opacity and therefore could affect also what we can get in terms of mixing and evolution of the AGB stars?
Never thought of that. Yeah, it's a good point. Yeah, because especially these hypernova, that's what we see. Yeah.
Maybe something new.
Mm-hmm.
Include?
Well, that's something to think about. But it's interesting. Well, it has to be seen how much we produce so that it can really have an impact on the thermal structure of the star. But it's interesting. Simon was first.
Have you looked at the light elements as well to see how they're tracking against the?
Yes. We've looked at that. We tend to produce some lithium in those stars with this Gaussian Fowler mechanism. We just spotted those species. We haven't really looked into the details. We compare now the C12 or C13 ratio, compare them to some limited observations. It can vary. I mean, depending on the overshoot parameters, that can give you a little bit of freedom to play with those. But one of the signatures now is the production of lithium. Yeah, they tend to produce some lithium, those stars, quite substantially. Yeah.
And are we seeing lithium in the?
Sorry?
Are we seeing lithium observationally?
I think you have to go to the UV, no? I don't know. I'm not an observer. Can't tell you.
Just following up on this diagram, is it a continuum? So if you had a neutron density of 10 to the 18 or 10 to the 20, would you land somewhere between the red and the blue curves?
Well, there are some lines. Those vertical lines, they have. That's where you have these neutron closures. Those are magic numbers. So you will eventually end up. I think if you change the neutron density, then you will shift. Yeah, eventually, there should be some kind of transition.
But it's the point that you just can't find an environment with
exactly
neutron density of 10 to the 18. So.
Yeah, exactly. It's either very large or intermediate, but it hasn't been found. But I think in terms of nucleosynthesis, you would find exactly the same byproducts. Yeah.
With your comparison to the high metallicity saga database,
Yeah.
you got that plot. Yeah, is that? I guess that's overshoot enabling.
Yes.
Overshoot's varying then.
Yeah. Yeah, it was just done before the talk, so I don't have all the labels yet. But also, yeah, if you can also change that a little bit if you take into account the nuclear uncertainties. Let's say you can recompute. That's a test we did to recompute one of these models with a different set of input nuclear physics. And you can have these, between 0.3, 0.5 dex change. So let's say a track that is here or here may end up, because of the change, may end up here. So you would have a dilation curve that goes like this. Yeah, that's something we did not do systematically, but we're already quite happy if that covers most of the observations.